Hello students, welcome to this second lecture of the kinetic theory of gases and the radiation. Now we will be proceeding the next part of the chapter. Now students, the next part we have to see is the interpretation of temperature in kinetic theory. Now already we have derived the equation, that is 3.10, which is pressure is equal to 1 by 3 into N by V mv square bar. Now by using this equation we can write it as the PV is equal to 1 by 3 N into m v square bar. So we have just rearranged this equation. So this may be further written as 2 by 3 N into bracket 1 by 2 mv square bar. Now the quantity half mv square bar is the average translation kinetic energy of a molecule in an ideal gas. The molecules are non-interacting and hence there is no potential energy term. Thus the internal energy of the gases is the purely kinetic. So the average total energy is equal to N. Thus we can further write as PV is equal to 2 by 3E. Now by using the ideal gas equation, which is P1V1 is equal to P2V2, which may be written as the PV is equal to N into Kb into T is equal to 2 by 3 E. Now the E will be written as the 3 by 2 N into Kb into T by rearranging this equation. Now this may be further written as the E by N. After rearranging we can write also as E by N is equal to 2 by 3 Kb into T. Now we can say that this means that the average energy per molecule is proportional to the absolute temperature T of the gas. This equation relates the macroscopic parameter of the gas T to the kinetic energy of the molecule. Now students, the next part of this chapter we are going to see is the law of equipartition of energy. Now we have seen that the kinetic energy of a single molecule is K is equal to half mvx square. So m is the mass of that particular molecule and vx is nothing but the velocity along the with respective to the x axis. So it may be given as the K is equal to half mvx square plus half mvy square plus half mvz square. So for the gas at the temperature T, the average kinetic energy per molecule denoted as the Ke is equal to half mvx square plus half mvy square plus half mvz square. Now but we know that the energy per molecule is 3 by 2 kBT. Now since there is no preferred direction x or y or z, so the mean half mvx square is equal to mean of half mvy square is equal to mean of half mvz square is equal to half into kb into t. So this is the expression that we can derive for the mean energy associated with the every component of translation kinetic energy, which is quadratic in velocity component in x, y and z direction is half kbt, and therefore the total translation energy contribution of the molecules is 3 by 2 kb into t. As it is 3 degree of motion, so it is 3 by 2 kb into t. Now students, we have to see the degrees of freedom. So we can see the molecule as a whole is free to move from one point to other point in the dimensional space. Now if it is restricted to move in the plane surface which is two-dimensional, there will be two coordinates x and y will be the sufficient for the describe the location of the component vx and vy. Now if a plane molecule moves along the straight line, the only x coordinate and the only one velocity component vx will be sufficient to describe the location and the motion along the straight line. We can say that the molecule is free to execute the 3 to 1 dimensional translational motion above the example from the above example. Now in the other words, the molecule in the example has 3 to and the 1 degrees, that the degree of freedom. So Thus we can say the degree of freedom of a system are defined as the total number of coordinates or independent quantities required to describe the position and the configuration of the system completely. I will repeat one more time. The degrees of freedom of a system are defined as the total number of coordinates or the independent quantities required to describe the position and the configuration of the system completely. So this is the degrees of freedom. Now here in this diagram you can see two independent axes Z and Y of the rotation of a diatomic molecule such as O2 lying along the x-axis. Now the monoatomic gas like helium contains the helium atoms, and helium atom has the three translational degrees of freedom. Like consider example of O2, that is oxygen, or the you can say the nitrogen, having the two molecules which two atoms like, and the molecule has three translation degree of freedoms. Now in addition you can say that it can be rotated around z axis and y axis. Figure 3.2, that is you can see on your screen, it indicates that likewise the rotation is possible along the y axis, and in general the diatomic molecules of rotate about its center mass in two directions are perpendicular to the molecular axis. Now the molecules like O2 are therefore said to possess the two additional degree of freedom, namely two rotational degree of freedom. Each of these two degree of freedom contribute the rotational kinetic energy. It can be shown Iz and Iy. Thus the inertia about x and y, the inertia about z and y axis with angular motion or the angular velocities or the angular speed omega z and omega y. Now the respective angular speeds, the rotation kinetic energies will be half Iz into omega z square and half Iy into omega y square for rotation around the axis. Thus for inertia about z and y axis with the angular speeds omega z and omega y we have seen. Now thus the total energy due to the translational and the rotational degree of freedom is given as the total energy, that is energy due to the translational degree of freedom, and the energy due to the rotational degree of freedom may be given as half into mvx square plus half mvy square plus half mvz square. So the total may be given as, again there is addition of half Iz omega z square plus half Iy omega z square. So thus above expression contains the quadratic terms of correspond of various degree of freedom of a diatomic molecule. Thus the E means the total energy due to the translational degree of freedom plus total energy due to the rotational degree of freedom plus the total energy, that is the vibrational degree of freedom. The term E is the vibrational, consists of the two contributions, one of the kinetic energy terms and other is from the potential energy term. So the energy due to vibrational may be given as half mu square plus half kr square, while where the u bar is the velocity of vibration of the atoms of the molecules, and the r is the separation between the atoms performing oscillations, and the k is related to the force constant. The term equation you can see, that is half mu square plus half kr square, are the quadratic in velocity and the position respectively, and each will be contributed. Now students, the next part we will see is the specific heat capacity. Now you may have learned that when the temperature of a gas is increased, even a small rise, it causes the considerable changes in its volume, that we have seen in the thermodynamics chapter. Now the volume and pressure is also changes. Therefore two specific heats are defined as, for the gases, namely specific heat at the constant volume Cv and specific heat at constant pressure Cp. The Mayer's relation gives an expression that connects the two specific heats, that is the Cv and Cp. Now for the explanation of the Mayer's relation, consider 1 mole of ideal gas that is enclosed in the cylinder by light. Frictionless, airless piston, let P, V and T be the pressure, volume and the temperature respectively of the gas. If the gas is heated so that its temperature is raised by small amount of delta T, that is dt, but the volume remains constant, then the amount of heat supplied to that gas dQ1 is used to increase the internal energy of the gas dE. Now since the volume of a gas is constant, no work is done moving the piston. Now as you can see here that the total work done, that is d small amount of work done dQ1 is equal to dE, that is total internal energy will be increased, which will be equal to CV dt, means the specific heat constant and the small amount of temperature will be dt. So its a product will be the small amount of work done dQ1, where the CV is the molar specific heat constant. Now on the other hand, we can see that if the gas is heated to volume of a gas increased by amount say dV, means we have considered here if the gas is heated to the same temperature at the constant pressure, then the volume of gas is increased by amount dV. The amount of heat supplied to the gas is used to increase the internal energy of the gas as well as to move the piston backward to allow the expansion of gas. So the work done may be given as dW is equal to PdV. So this type of work done, that is dQ2 is equal to dE plus dW, which may be given as Cp into dt. Now here students, the Cp is the molar specific heat of the gas at a constant pressure, but the dE is Cv into dt. Now from this equation we can say that the internal energy of ideal gas depends only on its temperature. So the Cp into dt is equal to Cv into dt plus dW, or you can say that the Cp minus Cv into dt is equal to P into dV. So this is how we can say that for 1 mole of gas the PV is equal to RT and the PdV is equal to R into dt. So Cp minus Cv is equal to R. This is known as the Mayer's relation between the Cp and Cv. Cp minus Cv is equal to R is nothing but the Mayer's relation between the Cp and the Cv, and this equation relation has been derived to assuming that the energy and heat energy and the mechanical energy work done are measured in terms of same unit. So generally heat supplied by the measured calories and the work is measured in joules. So the joule is the mechanical equivalent of the heat. So students, we will repeat once again that the Cp into dt is equal to Cv dt plus dW, which is equal to Cp minus Cv into dt, that is small temperature dt is equal to P into dV. That P into dV will be that pressure into that volume. Now for 1 mole of gas the PV is equal to RT, so P into dV is equal to R into dt since the pressure is constant. Substituting this value in equation we can get Cp minus Cv into dt is equal to R dt. So the Cp minus Cv is the R, and this relation is known as the Mayer's relation between the Cp and the Cv. Now student, we will think the same one for the monoatomic gases. For a monoatomic gas enclosed in a container held at a constant temperature T and the containing Na atoms, each atom has the 3 translational degree of freedom. Therefore, average energy per atom is 3 by 2 kb into T, and the total internal energy per mole is given as E is equal to 3 by 2 Na into kb into T. Now the molar specific heat at the constant volume is given as Cv is equal to dA upon dt is equal to 3 by 2 Na into Kb, which may be given as 3 by 2 into R. So the same concept we will held for the diatomic gases. For a gases consisting the diatomic molecules like O2 and 2 enclosed in a container held in a constant temperature T, if the treated as the rigid rotator, each molecule will have the 3 degree translational and the 2 rotational degree of freedom. Now according to the law of the equipartition of energy, the total internal energy given as E is equal to 3 by 2 Na into Kb into T plus 2 by 2 Na into Kb into T is equal to 5 by 2 Na into Kb into T. The molar specific heat at constant volume will be Cv is equal to 5 by 2 Na into Kb, which will be is equal to 5 by 2 R, and from this equation the Cp will be 7 by 2 R, so gamma is equal to Cp by Cv is equal to 7 by 5. Now, for diatomic gases containing non-rigid vibrating molecules, it can be given as E is equal to 3 by 2 Na into Kb into T plus 2 by 2 Na into Kb into T plus 2 by 2 Na into Kb into T is equal to 7 by 2 Na into Kb into T. The molar specific heat at a constant volume will be Cv is equal to 7 by 2 Na into Kb is equal to 7 by 2 R. So the above equation may be written as the Cp is equal to 9 by 2 R, which is the gamma is equal to Cp by Cv is equal to 9 by 7. So this is how we can derive the equation for the diatomic gases. Now students, the next part of this chapter we will see in the next video. Thank you so much.